Hello everyone, my name is Chirag Patil and welcome back to my YouTube channel. So in today's video, we will understand and implement VGGNet, right, which is a type of convolutional neural network. So in previous video, we had understand LXNet and implemented it using PyTorch, right? So if you haven't seen that video, I would recommend please go back and refer that video. It will help you to understand VGG and compare that always, right? Because LXNet was introduced in 2012 and this is, I would say it is a successor of it and performing very well than the LXNet and introduced in 2014. So let's get started. So first of all, VGG network is typically a convolutional neural network architecture that was proposed by Visual Geometric Group. So that's why it is called VGG, Visual Geometric Group, right, in 2014. So this network achieved excellent performance, but it got a second rank. It is not a first rank model, or it is, you can say it is a runner-up model, but it is very famous due to its simple architecture, right? So if you see this result of ImageNet challenge, right, in 2014, so you can see VGG had second rank. The first was GoogleNet, right? So we will see in upcoming video GoogleNet as well, but as of now, let's understand VGG, right? So VGG16 and VGG19 model are still often used as a benchmark for other deep learning model, okay? So what is the benchmark? So benchmark is basically nothing but whenever you are starting some problem, you have to start from somewhere, right? Let's say you are building one classification model for image classification, okay? So you will use this VGGNet first. Let's say this VGG is providing 80% accuracy, right? Then 80% is your benchmark. Now you need to improve the accuracy from 80% using different techniques, different model or different processes, right? So it is used as a benchmark as well. And even like it was introduced in 2014, now we are in 2024, right? After a decade, still it is used for a transfer learning kind of thing. Transfer learning is nothing but, let's say you have one model, it is VGG19 already pre-trained on ImageNet or large data set, right? So you can use that pre-trained model to perform some related task, which is you can train that model on the your particular data set, but it's already pre-trained on something, right? So it know how to understand the image and then you can refine the output further. So we will understand in upcoming videos what is the transfer learning, how it works. So currently you can think it's like we are using already trained a model to perform a related task, okay, simply. So let's move to understand the architecture of this VGGNet, then we will implement. So first of all, as I say, it is very known for its simple architecture, okay. So you can see it is using 3x3 convolutional filter, okay, throughout the network. So if you see the VGG16, it contains like 13 convolutional layer, but each convolution layer has fixed kernel size 3x3 and stride is 1 and padding is also we are using a same. So any convolutional layer in VGGNet will not change your output shape basically, right? So that's why it is simple. In LXNet, we are using 11x11 kernel size in first layer of the convolution, right? Then we are gradually decreasing it. Then we are using 3x3, I think. Okay. So this approach enables network to capture more complex feature. As like this kernel size 3x3, it will look a smaller part of the images and you can extract the complex feature as well, right? And computational cost will be also less because we are using 3x3 kernel. If you are using 11x11 kernel, it would be 121 features, right? And 3x3, it will be only 9 parameter to learn, right? So let's understand in depth what are the each convolution layer and each other layer are doing in VGGNet, right? So first of all, convolutional layer, as I mentioned, it using 3x3 convolution filter, which is smaller in the size compared to larger filter size. As I say, LXNet using 11x11, right? And all convolution layer will use padding same and stride 1 to preserve spatial dimension. So model, our convolution layer will not change the input size, right? Because we are using padding is equal to same and stride is 1, right? And the pooling layer, so all pooling layer will has kernel size 2x2 and stride is equal to also 2, right? Which help us to reduce the spatial dimension, right? I will explain in the when we see the this diagram or table how the size is reducing, okay, in the depth. So you know that VGG stands for Visual Geometric Group, right? So what does this 11, 13, 16, 19 means, right? So this is nothing but the layer of learnable layer in the network. So let's say if I am talking about the VGG16, which we will implement in this code. So VGG16 has 16 layers, which will learn something, right? So 16 layer means 13 layer will be a convolutional layer and 3 layer will be fully connected layer, right? We had seen what is the convolution and what is fully connected layer in LXNet as well, right? In LXNet we were having 5 convolutional layer, and here we have 13 convolutional layer, right? If we go for VGG19, you will have 16 convolutional layer. So one of the major difference you can say, it is the depth of this network from the LXNet, right? And second thing, we are using same kernel size for all convolutional layer. Okay, so after this convolutional layer, we have fully connected layer, simple, right? And we are using ReLU as an activation function to introduce non-linearity. And at the end, we have softmax function, right? Simple. So if you see this diagram, let me small this. Okay, yeah, little bit more. Okay, yeah, now you can see. So first of all, the VGGNet use image size is a 224 and it is RGB channel. Okay, so we will implement this one. If you see ABCD, then we are implementing this D convolutional layer. All the convolutional layer followed by fully connected layer, right? So if you see this diagram, they started from 11 layers, 13 layers, 16 layers, and then, right? So they are using local response normalization in this 11 weight, then 13 weight, but majorly good performing model is this 60 weight and 19 weight layers. Okay. So this bold line basically says we are adding new layer, right? So if you see here in 11 layer, there is no this convolution layer, right? And here this convolution layer is added. Here as well, this convolution layer added. Okay. So if you see, first we are using this con3 means 3 cos 3 kernel size. Okay. And 64 means number of kernel which we will use, right? Basically our out channel in our PyTorch term if we talk. Okay, so first we will use 2 convolutional layer followed by of course ReLU, and then it was kernel was 3 cross 3 and number of kernels are 64. So after this 2 convolution layer, our output will not change. Our output will be 224 cross 224 cross 64 because 64 is number of kernels, right? After we are applying max pooling here, so max pooling we are applying 2 cross 3 kernel and stride is equal to 2. So our max pool layer will change our input size into half. Okay, so here you will have 224. After max pooling you will receive 112 cross 112 size. Okay, so after we are applying 3 convolution, then again max pooling, then 3 convolution, then again max pooling. So at each max pool layer, our output size will be reduced by 2, or you can say we are converting into half size, right? Okay, and then at the end, after max pooling, we have fully connected layer, 3 fully connected layer, and then softmax, right? So let's basically implement it. Let me start. So as you know, we had used torch view in LXNet to visualize the model, and these are the some library which we will use, basically torch. So let's start to implementing. So let's say class will be VG16. We need to write nn.module. Let's define constructor. Self. Let's provide number of classes here. Okay, so it will be by default 1000 because ImageNet has 1000 class. Okay, and let's say dropout as well. Like this, dropout will be, let's say 0.5. Okay, let's provide some typing hint. Number of class will be integer, right? Now let's call module class in constructor. So we'll pass, let's say VGG16 self.init. It would be thunder init, right? Let's say init, right? Simple. So now, as we had implemented in LXNet, first we will implement feature model and then we will use as a classifier. So feature basically nothing but we will apply use all the convolutional layer in feature, and then fully connected layer will be in the classifier, right? So let's say self dot features will be nn dot sequential, right? And now let's start. So first we know our input size. Okay, so let me comment here, input shape will be, let's say 3 cross 224 224, as PyTorch works on a channel first, right? So we are writing channel first here. So now let's say nl.con2d. So our input channel will be 3 because our input image has 3 channel, right? RGB. So first we will use, so if you see here in the diagram or table, first we will use 64, then 128, then 256. So gradually it is increasing the number of kernels, right? Here out channel basically. So 64, then 128, then 256, then 512, right? So let's write that. I can write me like this. In channels would be 3, out channels would be, let's say 64, then kernel size would be 3, right? And stride would be 1 by default. We are not applying padding, so padding would be, sorry, we are applying padding, so padding would be same, so output will not change, right? And then we apply relu. Let's apply in place is equal to true, right? So this is one thing. So if you see in the table, we had implemented this con364 first, then second layer is same as the first, right? So let's copy it and we will simply paste. So when we write the code, we can understand how easy it is, the architecture, right? And now if you see after 2 convolutional layer, here input channel will be changed to 64 and output will remain as a 64, right? Kernel size will be same, padding would be same, and then we will apply max pull, right? Let's say max pull 2d. Okay, here will be comma max pull 2d. We will apply kernel size will be 2 and stride will be 2 as well, right? So if you see, when we apply max pull with stride 2 and no padding, it will convert our output size into half, right? So here we will have output size of 64 is number of channel, right? Sorry, 64 will be number of channel. Our output input was 224, so it will convert it into 112, right? So this will be our output. So if you see in the table, we had created this part, convolution 364, convolution 364 and max pull. Now we need to same operation with 128, right? So I will utilize this same code, right? No need to write again. So we will copy and paste. Okay, so if you see, here should be a comma and let's put it. Okay, so now your input channel will be 64 and we are converting into 128, right? Basically we are converting into double size, right? So let's say 128 input, your output will be also 128, and we are applying relu, and now our input size will also converted into half, so we will receive 56, right? 56 to the 112, right? So now we had created this second part as well, convolution 3 128 and max pull. So this basically this diagram is taken from paper itself, right? I haven't created this, so it is from the paper. So if you see this paper are very precise and explaining everything, how they are implement this model, right? So this is the very good part about this paper. Alex and also explaining everything in detail, right? So this diagram we are implementing currently. So now we have 128. Now we have 3 convolutional layer with 256 kernel number of kernels, right? As I say, kernel size and padding would be same for all. Just we are changing out channels or number of kernels, you can say, right? So let it be comma here, and here it will be 128, and now we are converting into 256 number of channels or number of kernels. It will be 256, and if you know there is a 3 convolutional layer, right? And then we are applying the max pooling. So here it will be a same, right? So here our output also change into 28 comma 28, right? Simple. So then we had reached till here. Okay, so now we will convert it into 512 3 convolutional layer with 512 number of kernels, right? So let's me copy this all the thing. We can modify this code as well using for loop as well, but I am writing here so we can understand it is architecture and it is very simple to implement as well, right? So input will be 256, then we are converting into 512, here will be 512, right? So now we reached here 512 till now we will apply max pool, right? So here we will get the output of 14, right? Because at each max pool layer with stride 2 we are dividing our output by 2, or output share will be half, right? So same thing, this will be our last convolutional layers, right? So if you see, as we are calculating VGG16, right? So it will have 16 convolution, like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. 13 convolutional layer and 3 fully connected layer. That means it has 16 layers, right? So let's implement last 3 convolutional layer followed by max pool. So we will utilize same code block, there is no change, right? Here it will be 5 and 2. As we are using padding same, there is no change in the output. Max pool will always convert your output size in divided by 2. So now we will have 7, right? Sorry, here we will change the label, the channel will change because we are passing 5 and 2. Here also it will be 5 and 2. Here it will be 2, 5, 6, and here it will be 1, 2, 8. Because we are increasing a number of kernel and decreasing size using max pool 2D, right? So yeah, the feature block is created. If you see this one, this part is called as a feature block, and we calculated till max pool, right? Now we need to create 3 fully connected layer. Okay, so let's write, okay, I need to press tab, yeah. Self dot classifier will be self, sorry, it would be nn dot sequential, and we need to create, right? So as we know, we had created max pool, right? So here we have output of 512 7 cross 7, that's it. And now sequential we will use linear layer, but in forward method we will use flatten and then we will apply the sequential, right? Because sequential model is a linear layer, can't apply directly on this matrix light output, right? Okay, so let's first apply a linear layer, nn dot linear. Linear layer also will be followed by a ReLU activation function. So in whole neural network, in all VGG16 19, we are using a ReLU as an activation function, or you can say providing non-linearity function, right? So let's say, so now linear layer input will be, let's say, what it take in features, yeah. So it will be, we know the output is 5 and 2 7 cross 7. Now we will flatten it, so we will receive 5 and 2 into 7 into 7, right? And out features will be 4096 because they have mentioned that, right? 4096 4096 2 times, right? Let's apply now ReLU. Let's say in place is equal to true. Okay, so now if you see, after that in the paper they are mentioning they use a drop down layer, right? So let me provide that information, right? Okay, so here they're mentioning the dropout regularization. So as we know, dropout also work as a regularizer, or you can say preventing overfitting, right? Let me a little bit zoom it, right? So it will help. Okay, so they are mentioning the dropout regularization for the first two fully connected layers, right? So training was regularized by weight decay, which is L2 regularizer, and dropout regularization for first two fully connected layer, right? So we have basically three fully connected layer, and this is a first of them. So it will require a dropout, right? And dropout is also used 0.5. So if you see ahead, yeah, dropout ratio set to 0.5, right? So we will use that. So let's say nn.dropout, and we will provide p is equal to, we had already passed in the argument, right? So it will be dropout. So this is our first linear layer or fully connected layer. Now let's build second would be the same. Okay, it will be linear layer, ReLU, and then dropout, because paper says first two fully connected layer has dropout layer. Okay, so in feature will be our 4096, out feature will be 4096, ReLU, and then dropout. Okay, same. So now our last will be nn.linear, and we are applying number of classes. Let's say first of all in feature will be 4096, and out features will be number of classes, right? Which we had defined here. Number of classes is 1000 by default, right? So this is about the classifier. So you can apply here softmax activation function here next as well, or you can apply it when we are doing the training part, right? So I am not applying here currently, so we will utilize this. Okay, so let's say, okay, so still I'm missing the comma. Okay, yeah, so it will work. So now we need to define forward method, right? So as we know in PyTorch, when we are creating the model, we require the init and the forward. Forward method is basically calculate the forward pass, right? So let's say define forward self, it will require the input and return the output, right? So first of all, we will create, let's say x is equal to self.feature, and we will pass x. So this will return this output, right? After the max full 2D 512 cross 7 cross 7, right? So now we need to flatten it. So let's say x is equal to, so we will use torch.flat, or you can resize as well. So in LXNet we had used flatten. Here let's say use the resizing kind of thing. So we will use the view. Let's say view x.size. The size is basically we are using the first step, right? Size of 0 and into -1. Okay, so 0 is basically a batch size. When we apply like forward pass, we have at least one batch, right? 1 comma something. So here we are creating the 1, and rest will be flattened. Okay, so let's say if you are having a 5 batch size, so you will receive 5 shape of 5 comma this 512 into 7 into 7 output, right? And if you have 1, then 1 comma this one, right? So we have flattened this. Now let's say x is equal to self.classifier, and we will pass this x here. Okay, and return this x. So this is about VGG16, right? So we have used a 13 convolutional layer and a 3 fully connected layer, right? So let's see. Okay, invalid syntax, perhaps forgot comma. Okay, so I think it is the common mistakes for me, which I do generally. Yes, here it should be a comma, here it should be a comma, here also we required comma. As we are copy pasting this code, we forgot that comma, right? Let's run and check. Yeah, now it is working. Okay, so let's say VGG model is equal to VGG16, right? Okay, unexpected in feature, it should be in features, right? So let's say where we passed, okay, here it should be features. Let's run. Yeah, so model is basically created. Now let's upload this model to visualize how it is providing its shapes, right? So we are using that torch view library. If you see here, I had installed and imported torch view, and from torch view I am imported draw graph, right? So let's say draw graph, we need to pass model, which will be our VGG model, and input data. To visualize, we are passing 1, 3, 224, 224. This is our input size, right? So it should be not input data, it should be input size. Okay, so it will return one object, I think. Yes, we need to visualize it, right? Let's say visualize graph. Yeah, okay. So let me provide nested we can visualize both sequential and feature. It is currently in the straight direction, it also showing everything, but let's see. Nested, show nested, or what was that? I forget about it. Like, let me check. It is like expand. Yes, expand nested, right? Let's say true. So let's see. Yeah, so now you can see first is our sequential model, okay, which is our feature extractor, okay. So you can see we are passing 2 to 4. Then after max pooling, if you see here, our shape was changed from 2 to 4 to 112, right? Then 112 to 56. Then after applying the max pooling, we reach at 28, and so on, right? After that, we are applying fully connected layers, and followed by ReLU and dropout, and then at the end we have 1000. So this is basically a whole architecture about the VGGNet. So if you compare with the LXNet, there are majorly 2 points. First is the depth of this VGGNet is increased drastically, we can say, because in LXNet we are using only 5 convolutional layer. Here we have 13 convolutional layer. If you use VGG19, it is around 16 convolutional layer, right? And second thing, we are using a same kernel size and make it very simple and able to extract the complex detail as well, due to its depth and smaller convolutional kernel size, and number of kernels will be increased, right? So one thing you can do, you can implement VGG19 and check how it is going, right? So this is all about the VGG16. If you have any doubt, you can ask in the comment section, we can discuss there. If you like this video, please press the like button and subscribe my channel for more content. Thank you.